Okay, for the design parameter. So first, ride dynamic deal with how the car interact with road surface, vibration, and ensuring passenger comfort. If racing comfort is balanced with performance, since it's an EV, electric car, so factor like battery weight and placement might affect the dynamic. So the user need critical design parameter and constraint. So parameter could include suspension stiffness, damping coefficient, tire characteristic, vehicle weight distribution, and chassis rigidity. Constraint might be weight limit, space for component, safety standard, and integration with other subsystems like powertrain or battery system. So next, refining requirement. They need quantifiable target. For example, instead of comfortable suspension, a target vibration frequency range or maximum G-force experienced by the driver. So safety could involve ensuring the suspension can handle high load during cornering. Regulation might detect certain material strength or safety factor. So as you can see, the point, suspension stiffness is to tune to balance light comfort, low frequency, vibration, damping, and handling high frequency response. For damping coefficient, adjustable damping to optimize energy absorption across very low load. And for tire characteristic, spring rate, contact patch severity, and great dynamic load. For vehicle weight distribution, electric car specific constraint such as battery placement and affecting center of gravity. While for chassis rigidity is comparative with the SAE frame to minimize torsional flat. For ride comfort index RCI, target frequency range of 1 to 5 Hz for vertical vibration, ISO 261 standard. So this constraint for design parameter is weight total subsystem weight is equal to or more equal to or lower 15 kilogram SAE regulation. For space suspension geometry must interfere with battery pack, motor, and cooling system. Regulation comply with NSGV challenge rules such as material strength, safety, and factor. For integration, compatibility with telemetry system for real-time ride dynamic and monitoring. Lastly, for safety, maximum allowed G-force on driver lower or equal to 3G during cornering or braking. So next is for quantifiable requirement. So the total weight of the vehicle is 789 kg. So for weight distribution, its pole suspension must support 45% of total vehicle, which is 359 kg. For rear suspension must support 55%, which is 438.9 kg. So the wheelbase strength and compatibility, we use double wishbone suspension that align with 3,544 mm wheelbase and 4,000 mm thread weight to maintain optimal camber or toe angle. So center of gravity management suspension geometry must limit body roll to lower or equal 3 degree during cornering at lateral acceleration. So this calculate for SCG equal to 457.2. So center of gravity, this is vertical distance from the ground to the car center of gravity. Okay, so for weight distribution, this affect the load on the front and suspension. So the requirement will hold how suspension design accommodate this distribution to maintain balance and optimus ride comfort. So a higher COG or center of gravity can affect vehicle stability during cornering and braking. So the suspension system are managed with transport FFT to ensure safety and comfort. So for safety requirement is we have load capacity. Each damper must withstand 5 times static load such as the front damper. So will time 359 multiply 5, we get 1,795 at peak load. So for G-force limit, suspension must maintain tire contact patch stability up to 3G lateral acceleration. For ride comfort index, RCR target vertical vibration, so lower or equal 0.5 meter per second, adjust for vehicle weight and speed damper tuning. So suspension travel higher or equal to 50 meter to absorb bound without bottoming out, accounting for center of gravity height and dynamic weight transfer. Okay, next is for detailed design document outline based on chapter 2 slide. So we have product description, suspension system optimized for 780 kg electric car with 44 to ratio 55 weight distribution. For benefit deliver stable tire contact patch under 3G lateral acceleration. For assumption constraint, double wishbone design with load specific damping 359 kg via 438.9 kg. For product concept, fixed FCE frame 359 wheelbase 4,000 mm track weight. And for target market, Formula Student team amateur racing circuit.
My name is Dewa Shanikedi and my metric number is AN220105. So today I'm going to talk about the subtopic or the calculation for EV Racecar subsystem design project, which are the load transfer and the spring rate. Before we go to the calculation analysis for load transfer and spring rate, we have identified the importance of these two calculation analysis. The first one is the importance of load transfer analysis in a race car lies in its direct impact on the tire grip, handling balance, and overall performance. During acceleration, braking, and cornering, weight will shift dynamically across the chassis of the car. So this is known as the load transfer. Since the tire grip is not proportional to load, improper or uncontrolled load transfer can lead to grip loss and unstable hand. So by analyzing the load transfer, we as an engineer because it is directly influence how the vehicle will give response to the dynamic loads and maintain the contact of the tire with the surface of the track. And the spring rate will determines how much a spring can compress under load, which affect the ride height of the car, body roll, pinch, and the weight transfer characteristic during acceleration, braking, and cornering. Then I will start with the load transfer calculation analysis. For the load transfer calculation analysis, I use the traction circle theory that can be shown in figure 1. From the traction circle that shown in figure 1, we can identify the maximal longitudinal acceleration x and the maximal lateral acceleration ay are 1.2 and 1.4 respectively. Hence, we can find the final value of the ax and ay by using the equation 1 and equation 2 respectively. Then the table 1 shows the parameter of the EV Racecar that I used to do the calculation analysis for the load transfer. However, the maximum acceleration experienced by the vehicle is during cornering followed by braking, and the maximum acceleration can be obtained through equation 3. Equation 3 is based on the theory of Pythagoras theorem. And based on the equation 1 and equation 2, g is indicating the gravitational acceleration, which equivalent to 9.81 meter per second to the power of 2. Hence, the value of Ax and Ay are 11.772 meter per second to the power of 2 and 13.734 meter per second to the power of 2 respectively. Next, the value of Ax and Ay are substituted into equation 3, where the maximum acceleration during the cornering accompanied by the braking is equal to 18.0504 meter per second to the power of 2. The weight of the car is 798 kg. The static weight distribution involves the front area of the EV Racecar, which are indicated as WF and WR respectively. The calculation for the WF, which is the weight of the front, is shown below, and the value of WR can be obtained through the same working step. So the first step for the calculation of WF is using the ratio, which WF ratio to WR equal to 45 ratio 55. Then the Wf can be obtained, which the value equal to 359.1 kilogram. And then the weight on single wheel is in steady state for front and rear, which are denoted as Wf single and Wr single respectively, can be given by equation 5. And the value of Wf single is equal to 179.55 kilogram, and the value for the weight on single wheel for rear can be obtained by using the same equation, which is equation 5. After that, the total longitudinal load transfer must be calculated by using equation 6. Then if you take a look on the equation 6, the W is indicating for the weight of the car. The HCG is the height of the center of gravity to the ground, and AX is the maximum longitudinal acceleration. Then the value for the total longitudinal load transfer is equal to 121 and 82 kilogram. Besides, the total lateral load transfer need to be calculated, and the working step is based on equation 7. If you take a look at the equation 7, the W is equal to the weight of the car, the HCG is equal to the height of the center of gravity to the ground. Meanwhile, the AY is equal to the acceleration. All the value need to be divided by the track width, and the value for the total lateral load transfer is equal to 127 and 70 kilogram. However, the maximum load transfer can happen during cornering and braking, and it is known as the total diagonal load transfer. The value of the total diagonal load transfer can be achieved through the equation 8. We take a look at the equation 8. The total diagonal load transfer is equal to the square root of total longitudinal load transfer to the power of 2 plus total lateral load transfer to the power of 2, and the final value is equal to 178.49 kilogram. The value of the maximum load on the single wheel for front and rear can be calculated by the following equations 10. We look at the equation 10. The final value for the maximum load on the single wheel for front is equal to 356.04 kilogram. The value for the maximum load transfer for single wheel on the rear can be calculated by the same following step above by equation 10, and the result of the maximum load transfer for the single weight at the rear is equal to 396.44 kilogram. Then we are moving on to the spring weight calculation analysis. So our group is using the double wishbone suspension, and figure 2 show the schematic diagram of spring for one of the double wishbone suspension for our EV race car. First of all, we need to find the reaction force from the ground on the wheel by using the equation 11. Equation 11 is showing F equal to MA. Fine, and the dynamic factor of 2.1 is considered to find the dynamic force acting on the spring. The value of the dynamic force is obtained through the equation 13. So the formula for the dynamic force acting on the spring is equal to the spring force times dynamic factor. And the final value for the dynamic force on the spring is equal to 6,858.17 Newton. Finally, the spring stiffness can be calculated based on the equation 14. Equation 14 is showing the spring stiffness, which the equation is equal to F equal to Kx. F is the dynamic spring force, meanwhile X is the spring stiffness, and K is the deflection. The value of the spring stiffness of front is equal to 122.91 Newton per millimeter. The spring force and dynamic force acting on the spring for rear are 3,991.52 Newton and 8,382.19 Newton. The spring stiffness for the rear is 150.22 Newton per millimeter. The value for rear can be obtained by using the same working step. That's all for me. Thank you.
Warahmatullahi wabarakatuh. My name is Muhammad Akademish bin Muhammad Sufyan. So this is our first design for our concept for Formula SAE compatible electric racing car, which is a lightweight, single-seater performance machine designed for precision, agility, and efficiency. At its core, the chassis is a tubular space frame engineered for strength and minimal weight. The cockpit places the driver low and central, protected by a full roll hook for compliance and safety. The power comes from a rear-mounted electric motor driven by a compact high-output battery pack, positioned centrally for balance and weight distribution. What sets this car apart is its fully independent double wishbone suspension at all four corners. Double wishbone, also called A-arms, allow each wheel to move vertically with minimal camber change, improving tire contact during cornering. This results in exceptional handling position, reduced body roll, and better grip in both braking and high-speed turn, critical for FSAE competition. Simple aerodynamic features like the front splitter, side pod, and rear wing provide just enough downforce and cooling airflow without unnecessary drag. This is a purpose-built, balanced, and FSAE ready. This car is a true showcase of electric performance and smart engineering. That's all from me. Thank you.
Assalamualaikum, my name is Saki Kuan Makanan. My method ID is CN220352. This is the second design for our project, so I will compare the improvement that I did in this design compared to the first one. Okay, to achieve optimal handling and stability, the frame is designed to support a near 50-50 weight distribution by centrally positioning the driver and placing heavier components like the engine, fuel tank, and battery close to the vehicle's center of gravity, while maintaining symmetry for balanced load transfer. Okay, next is the design used a tubular space frame, which offer an excellent balance of lightweight, structure, and high rigidity, ideal for performance application. Okay, the next one is a well-positioned roll hook and upper frame provide essential driver protection, addressing key safety concerns. Okay, next is the frame layout allow clear mounting point for major components such as suspension, engine, and cockpit system, showing good integration planning. Why we choose double wishbone suspension? Okay, first is superior handling performance. Double wishbone suspension allow better control of wheel chamber during cornering, which maintain a maximum tire contact with the road and improve grip. Second is to improve ride comfort. Because each wheel can move independently, it absorbs bump and irrigative better, resulting in a smoother ride. Third is adjustability and turning. This function allow more flexibility in adjusting element setting like chamber, caster, and toe, which is useful in performance and motorsport application. The last one is better load distribution. Distribute force more effectively during acceleration, braking, and turning, reducing stress on the chassis.
You can see this is the table of customer consideration. There are various steps. For the first step is we must know the customer needs, where the relative importance for each need or want should be listed. For the second step is customer supplier compatibility, where this is the matrix expose missing, redundant and conflicting needs and capabilities. If there are problems, the VOC and VOS can be revised. For the third step, which is the competition, where a relative score is assigned for how well each design performs. This step indicates which need will be provide more competitive advantage. And for the interaction, which is step 2B, which is explain about the feature correction matrix, show interaction between design features. For the next one, added underneath, supplier compatibilities. This one explained about this should not focus on individual specification, design, concept, and embodiment. And then for the last one is the evaluation matrix, where it explained about, at this point, very difficult step because it can be simplified by revising the VOS, because this step scores each supplier compatibility for the design. And the last step is step 5, priority calculation, where the scores are combined and determine which capability should be prioritized. The winner will receive more design effort to increase the overall performance. For this one, as you can see, this is the house of quality matrix of the EV Racecar suspension subsystem design, where it relates the customer requirements such as handling, ride comfort, durability, weight, and serviceability with the handline, spring rate, material strength, mass, and suspension travel, and also acceleration. As you can see, there are various points on the strong and moderate for each point.